Chapter 7, Dimensional Analysis, Similitude, and Modeling. Dimensional analysis is a way of seeing order and complexity. Many fluid phenomena depend on several variables at once: geometry, velocity, density, viscosity, gravity, surface tension, pressure difference, and more. If we try to study every variable independently, experiments and correlations become overwhelming. Dimensional analysis reduces the problem by grouping variables into dimensionless combinations that express ratios of physical effects. The method begins with dimensional homogeneity. A physically meaningful relationship must be expressible without depending on arbitrary units. If changing from meters to feet changes the structure of a physical law, something is wrong. This principle allows variables to be combined into dimensionless groups. These groups are not random algebraic tricks. They are compact statements of competing forces, transport mechanisms, or geometric ratios. The Buckingham pi theorem provides the formal structure. If a phenomenon depends on a certain number of dimensional variables, and those variables involve a smaller number of independent base dimensions, the relationship can be rewritten using fewer dimensionless groups. This does not solve the physics automatically. Instead, it tells us the proper form in which experiments, measurements, or numerical results should be organized. It turns a many-variable problem into a smaller and more meaningful map. Several dimensionless groups appear again and again in fluid mechanics. The Reynolds number compares inertial effects with viscous effects. The Froude number compares inertial effects with gravity effects and becomes central in free surface flows. The Mach number compares flow speed with acoustic speed and tells us when compressibility becomes important. The Weber number compares inertia with surface tension and matters for droplets, sprays, bubbles, and small-scale interfaces. The Euler number relates pressure effects to inertia and appears naturally in pressure drop and force correlations. Similitude is the bridge from model to prototype. Geometric similarity means the model has the same shape as the real object, scaled in size. Kinematic similarity means the patterns of motion correspond. Dynamic similarity means the relevant force ratios match. A model study is reliable only when the dimensionless groups controlling the physics are matched, or when the mismatch is understood and judged acceptable. A model that merely looks like the prototype may still produce the wrong flow behavior if the controlling dimensionless numbers are different. Sometimes it is impossible to match all similarity requirements at once. A wind tunnel model may struggle to match both Reynolds and Mach numbers. A river model may prioritize Froude similarity because gravity waves dominate, while accepting imperfect Reynolds similarity if viscous effects are secondary. This is not a failure of dimensional analysis. It is one of its strengths. It tells the engineer which compromises are being made and which physical effects may be distorted. The deepest lesson is that scaling is thinking. Chapter 8. Viscous flow in pipes, laminar, turbulent, major, and minor losses. Pipe flow is one of the most common and practical settings in fluid mechanics. Water distribution systems, oil pipelines, blood vessels, cooling loops, hydraulic circuits, ventilation ducts, and chemical process lines all depend on the motion of fluid through conduits. Unlike the ideal streamlined flows introduced earlier, pipe flows are dominated by viscosity, wall friction, turbulence, and losses. The central engineering question is usually straightforward. How much pressure or head is required to drive a desired flow rate through a given system? The wall controls the story. Because of the no-slip condition, fluid at the pipe wall has the same velocity as the wall, which is usually zero. Moving away from the wall, the velocity increases. This variation creates shear stress and dissipates mechanical energy. Even in a straight horizontal pipe with constant diameter, pressure must decrease in the direction of flow to keep the fluid moving against wall resistance. The character of pipe flow depends strongly on the balance between inertia and viscosity. At low Reynolds number, the motion is laminar. Fluid particles move in smooth layers with little mixing across the pipe. At higher Reynolds number, the flow becomes turbulent. Velocity fluctuates irregularly, mixing intensifies, and momentum transfer across the pipe becomes much stronger. For ordinary internal pipe or duct flow, engineering references commonly treat flow below about 2,100 as laminar, between about 2,100 and 4,000 as transitional, and above about 4,000 as turbulent. The exact numerical boundary should never be treated as a universal switch for every geometry, disturbance level, roughness condition, or non-Newtonian fluid. Laminar pipe flow has a particularly clear structure. In a circular pipe under steady, fully developed conditions, the velocity profile is parabolic. The fluid at the wall is stationary. The speed rises smoothly toward the center, and the average speed is lower than the centerline speed. Pressure drop is directly tied to viscosity, length, flow rate, and pipe size. Because viscous effects dominate the entire cross-section, ordinary wall roughness usually has little influence on laminar friction compared with its role in turbulent flow. Turbulent pipe flow is less orderly, but often more common in engineering systems. Turbulent fluctuations move momentum across the pipe more effectively than molecular viscosity alone. The result is a fuller velocity profile, with high-speed fluid extending closer to the wall, but also a larger wall shear for many conditions. Surface roughness can protrude into the near wall region and increase resistance. At sufficiently high Reynolds number, friction may depend strongly on relative roughness, and only weakly on Reynolds number. Minor losses are losses caused by components, rather than by long straight pipe. Entrances, exits, elbows, T's, valves, filters, contractions, expansions and fittings all disturb the flow and dissipate energy. The word minor can be misleading. In a short system with many components, these losses may dominate the total required head. Each component is often represented by a loss coefficient, allowing its effect to be expressed in terms of the local flow speed. Pipe systems combine the energy equation with major and minor losses. A single pipe problem may ask for the flow rate produced by a known pressure difference, or the pressure drop required for a known flow rate. Multiple pipe systems introduce branching, parallel paths, and networks. The flow distribution must satisfy both mass conservation at junctions and energy consistency around paths. Because the friction factor may depend on the unknown flow rate, many real pipe problems require iteration. Chapter 9. Flow over immersed bodies. Boundary layers, drag, lift, and separation. External flow occurs when a fluid moves around a body rather than through a closed conduit. Air around a car, wind over a building, water around a submarine, flow past a bridge pier, and air over an aircraft wing all belong to this family. The body is immersed in a surrounding fluid, and the engineer often wants to know the forces, moments, pressure distribution, and wake behavior. Viscosity plays a subtle role in external flow. Away from the surface, many high Reynolds number flows behave almost as if viscosity were small. Near the surface, viscosity is unavoidable because of the no-slip condition. The thin region where velocity adjusts from the wall value to the outer flow value is the boundary layer. Although it may be thin compared with the body size, it controls wall shear, separation, wake formation, and much of the drag. A boundary layer grows as fluid moves along a surface. Near the leading edge of a smooth, flat plate, it may begin laminar, with orderly motion and relatively low skin friction. Farther downstream, disturbances may amplify, and the layer may become turbulent. A turbulent boundary layer has stronger mixing and higher skin friction, but it also brings higher momentum fluid closer to the wall. This can help it resist separation under adverse pressure gradients. Thus, turbulence can both increase friction and delay separation, creating design trade-offs. Drag is the component of force in the direction of the incoming flow. It has two major sources. Skin friction drag comes from shear stress along the surface. Pressure drag, or form drag, comes from pressure differences between the front and rear of the body, especially when separation creates a low pressure wake behind it. A streamlined body is shaped to keep the flow attached and reduce pressure drag. A blunt body tends to separate more readily and can have a large wake, making pressure drag dominant. Separation occurs when the boundary layer no longer has enough near-wall momentum to move against an increasing pressure in the flow direction. The flow near the wall slows, may reverse, and detaches from the surface. Once separation occurs, the outer flow is displaced away from the body, a wake forms, and pressure recovery is reduced. This can greatly increase drag and create unsteady forces. Vortex shedding behind cylinders, buffeting of structures, and stall on wings are all connected to separation behavior. Lift is the component of force normal to the incoming flow. It arises from the pressure and shear distribution over a body, especially when the flow is turned or circulation is present. Wings, hydrofoils, rotating balls, sails, and turbine blades all rely on lift-like effects. An airfoil at a moderate angle of attack can create a pressure difference between its surfaces and turn the surrounding flow, producing lift. At too large an angle, separation becomes severe, and lift may drop sharply in stall. Chapter 9 connects the local viscous ideas of Chapter 6 with the scaling ideas of Chapter 7 and the momentum ideas of Chapter 5. It teaches that external flow forces are shaped by boundary layers, separation, pressure recovery, wake structure, and dimensionless coefficients. In practical design, the goal is often not to eliminate viscosity, which is impossible, but to manage its consequences.